The last set of data that I want to look at is an example of linear regression. So this is not categorical data, this is two continuous variables. So here I have something which is mass and T-cell, and it's to do with birds called black wheatears that have a mating ritual which involves carrying around small bits of stone during the nesting season. So what you have here is the mass of the stones that they carry around and the T-cell count that's been made of each of the birds. So somebody had to capture the bird, take a blood sample, do the T-cell counter, and also look at what size of stone they were presenting during their mating ritual. So which way around do we want to put the data? What's causing what to happen? Let's go down and just start the process of regression. So this is regression linear. So we have dependent and the independent variable. So the independent variable is not that independent. So that's the thing that's causing something to happen. It's the treatment variable. It is the variable that we're interested in. So in this case, it's going to be T-cell. It's the thing that we think specifies how fit the bird is, and therefore how capable it is of carrying out a bigger and more impressive mating ritual. The dependent variable is the mass that it's able to carry. So now I've got my model set up. Within SPSS, if I had more variables, I could add them in using to the independent variables and do multivariate regression. Now, the way they can be added in, there's multiple ways. You have enter, which is put them in one at a time in the order that they're listed in the independent variables. You can you can put them in stepwise. You can remove them, so start with all of the variables in and then take them out one at a time. There's lots of different ways that you can do this. We're just doing a single variable, so it doesn't matter. If you're doing more complicated variables, it is wise to try different ways of adding and taking the variables out, because they have odd effects on one another. So if two variables are related to each other, correlated to each other, if you put them in different orders, they will have different effects on the model when you take them out. You can calculate the statistics of this, and the only thing that I would suggest you put on there is the confidence intervals. If you're going to do very complicated models, you might also put the R-squared change in. There's something that does plots. We could do that, but probably I'm not going to. I'm going to do it using the save function instead. If you look here, you've got two columns, one which is mass, one which is T-cell. So what I'm going to do is, when I've fitted the line through my set of data, when I've fitted a gradient and an intercept, I'm going to do some predictions. So I'm going to predict the value of mass from each of these T-cell measurements that I've got. So this is what I actually observed. What I can do is predict from the equation that I'm going to get what the mass would be from each of these values of T-cell. I can also do something which is called calculate the residuals. So the residual is the difference between what I actually observed, this mass, and the unstandardized predicted value. So I want to calculate those. And these residuals can also be standardized so that they have a mean of 0 and a standard deviation of 1. Now they always have a mean of 0. The point of least squared fitting and producing a linear regression is that it has the minimum amount of deviation between the line and the points. So it goes so you have the same amount of difference above the line as below the line, so the mean difference has to be 0. But if you do standardize so that it goes between, you count the number of standard deviations above and below, it's easier to understand what it means. And that will do. Let's continue. There were some other things there which are Cook's distance and leverage, which I talk about in the lecture notes, but we don't really need to work out for the assessments. So I can press OK. As usual, SPSS creates quite a lot of output, more than you really want to look at. The first thing, it tells you what your model is. So T cell is your x-axis, and it's predicting your mass. Next thing, it tells you your R and your R squared. So your R is 0.578. It's not amazing, but it's not terrible. The R squared is 0.334, which means 33.4% of the variation in the amount of mass the bird is lifting is controlled by their T cell count, is related to the T cell count. That means another 67% is related to something else to do with the bird. Could be just general to do with size and other things like that. Next, you have the ANOVA table, which you can ignore apart from the SIG. So this is telling you that you have a slope in your line. It's not just a horizontal straight line with no slope on it at all. And then you come to the model itself. So you have the constant and you have T cell. So what I'm going to do is build a chart. I'm going to build a scatter plot, and I'm going to put T cell on the x-axis and mass on the y-axis, and I'm going to press OK. Now this is your standard plot that you would get if you were running this in Excel. So if I double click on it, I can click on this thing here which says add fit line at total, and I want a straight line, a linear one, so I could do put on linear, so fit the line, close. So it says the gradient of the equation for that line is y equals 3.91 plus 10.17 times x, and here's your r squared. So that's everything that we've seen before in the table. So the r squared was 0.334, in the picture it's 0.334. So here is your table of your regression. So the first thing it says is your intercept, your constant, is 3.911. So that coefficients, the values of your equation, are in this column which is labelled B. It stands for beta, but let's not worry about that. So the T cell count, because T cell is your x-axis, this is your gradient, because this tells you that if T cell goes up by 1, the mass will go up by 10.165. That's what a gradient is. If this goes up by 1, how much does y go up by? Now, it also gives you the significance using a t-test. Don't worry about how those are calculated for the constant and the T-cell. So this is telling you that both of these are pretty well modelled by the linear model. And then next, and most important of all, is this, the confidence intervals for the intercept and the gradient. So the intercept on average is at 3.911, but it could be anywhere between 1.584 and 6.239. And the slope, the gradient, is 10.165 on average, but it could be anywhere from 3.267 to 17.063. That's the confidence bound, the variability you can get in those values. If the confidence bound for the slope contains 0, so it can be negative or positive or contain 0, then you will not have a significant model. The values here will be way above 0.05, and you shouldn't reliably look at the model. Here are the residual statistics. So this is telling you that the residual, the minimum amount is -3, the maximum is 3.2, it's got an average of 0.000, which is fine, and the standard deviation is 1.389. Now, as I said, standardizing it so you've got a residual standard deviation of 1 makes life a bit easier, because what we're going to need to do is another couple of graphs. So first thing I can do is put the unstandardized predicted values onto it. So I can add these to the actual values that you observe. So now I've got a chart which will have two different colors. So one will be what you actually measured and one will be that calculated by the line. So if I press OK, now I get this plot, and you can see you've got T-cell mass and you've got the unstandardized predicted values, which are the ones that go all the way along the line. So those are in the dark green, and the blue ones are the actual values that you measured. So the difference between the green and the blue at each of these points is the residual. So sometimes it's negative, sometimes it's positive. So the other thing I can do is get rid of those. So on the x-axis I still want to keep T-cell, but what I want to do is put the standardized residuals on this as well, and press OK. So when I plot the standardized residuals, I'm expecting to see no pattern. If you get a random scatter above and below 0, so sometimes positive errors, sometimes negative errors, and they don't have anything like an up and down wave or a curve, then you've got a good model. But if you do it and you find a curve, then your data does not fit a line, it is a curve. These diagnostics are important to do if you're doing genuine science and you're fitting lines and you're fitting gradients and making predictions. You have to check the quality of your model. This is also revealing that this point here and this point here are very bad. So they're more than 2 standard deviations away from the mean in terms of residuals. So these points need to be looked at. You need to double check your data to find out if they are absolutely real, or possibly remove these two and then recalculate the line with those points removed. Doing regression without the diagnostics is really bad practice. So you need to remember to do the diagnostics, and that's the power of SPSS, because it makes doing the diagnostics pretty trivial.